All right, let's talk databases. If you've spent any time working with relational data, you know that getting your tables into Boyce-Codd normal form, BCNF, is pretty much the gold standard. It's supposed to be how we get rid of all those nasty data anomalies. But what if I told you it's not the end of the story? Let's get right into it. So you've done all the hard work. You've tracked down your functional dependencies. You've structured your tables perfectly to meet the strict rules of BCNF. You're thinking, I'm good, right? Your data should be clean, consistent, totally free from those annoying modification problems. But there's a really subtle trap hiding in there that can catch even the best of us. And today, we are going to spring that trap. We're going to look at a situation where a table that is 100% perfectly valid BCNF can still create a ton of data redundancy and lead to some really serious update issues. Okay, check out this table. At a quick glance, it looks fine. And here's the crazy part. Technically, it is in BCNF. Why? Because every single column, SKU, buyer, and buyer major, is part of the primary key. There's nothing but the key, so there are no partial or transitive dependencies for it to violate. The only thing determining the whole row is the whole row. So technically, it passes with flying colors. But here's where it gets weird. Watch what happens when we try to update it. Let's say we want to add a new product for Nancy Myers. We can't just pop in one new row. Nope. To keep the data consistent, we have to add 2 new rows, one for her finance major and another for her marketing major. You see the problem? We're being forced to duplicate information just to record a single new fact. That is a textbook insertion anomaly, and it's a massive red flag. And this is the absolute key to understanding what's going on. The issue isn't a functional dependency. BCNF handled all of those. It did its job perfectly. What we're dealing with is a whole different beast. It's called a multivalued dependency. This really gets us to the heart of the matter. So to fix this thing, we've got to understand what we're actually up against. What is a multivalued dependency? So a multivalued dependency, or MVD, pops up when one item, like our buyer, is tied to a whole set of values in another column, like her list of majors. But here's the kicker. That set of majors is completely independent of another set of values she's tied to, like the list of SKUs she's bought. The root problem is we've jammed 2 unrelated facts, what Nancy buys and what Nancy studies, into a single table, and now they're fighting each other. Let's put this side by side with what you already know. A functional dependency, the one with the single arrow, is simple. You know X, you get exactly one value for Y. You know the buyer, you know their one department. Easy. But a multivalued dependency with that double arrow is different. You know X, and you get a whole list of values for Y. You know the buyer, you get their entire list of majors. Okay, so if BCNF can't fix this, what can? Well, the answer is to go to a higher normal form. This brings us to the fix, 4th normal form, or 4NF. And you know what? The solution is actually super intuitive. It really just comes down to 2 simple steps. First, you identify those independent facts that are all tangled up. And second, you just pull them apart. Give each independent fact its very own table. That's it.
So here's our problem child one last time. We've got 2 different ideas mixed together. The products a buyer is associated with and the majors a buyer has. Let's untangle that knot.
And boom! Here's the fix. We just split that one messy table into 2 beautifully clean ones. The first table, buyer_SKU, does one job. It tracks who buys what. Simple. The second table, buyer major, does its own job. It tracks who has which major. Now, if Nancy buys a new product, we add 1 tiny row to the first table. If she adds a new major, 1 row in the second table. The anomalies, completely gone. Problem solved. Okay, that feels pretty satisfying, right? We've conquered functional dependencies with BCNF, and now we've handled multivalued dependencies with 4NF. So we're done, right? Is this it? Have we reached the top of the normalization mountain? Well, not quite. While 4NF is going to solve the vast majority of problems you'll ever encounter in the real world, there are a few more, let's call them theoretical, levels to explore. So let's take a quick peek at 5th normal form. 5th normal form, which you might also hear called project join normal form, is designed to deal with some really obscure data problems. We're talking about weird, cyclical constraints that can span across multiple tables. Honestly, the chances you'll ever actually need to implement 5NF are incredibly slim. For most of us, 4NF is the practical finish line. But if 5NF is for those super rare cases, what's the absolute theoretical endgame? What's the purest form of database design? Well, that would be domain/key normal form. Domain/key normal form, or dk/nf, is basically the holy grail of normalization theory. The guiding idea is incredibly elegant. A table is in dknf if every single rule about your data is a direct result of your keys and your domains. In other words, there are no hidden rules or weird exceptions. And if you can get a table to this state, it is provably mathematically guaranteed to be free of all modification anomalies. It's perfection. Okay, we've gone on quite a journey, haven't we? From a hidden flaw in BCNF all the way to theoretical perfection. Let's bring it all back down to earth with a single, actionable rule you can use every single day.
So let's recap. BCNF is really powerful, but it's not foolproof. It can hide those sneaky multi-valued dependencies that create all sorts of update headaches. Your practical solution is fourth normal form, or 4NF, which cleanly separates those independent facts. And yeah, 5NF and dknf are out there as the theoretical ideals, but if you walk away with just one thing today, make it this. You must always eliminate multi-valued dependencies from any table that's going to be updated. That is the crucial practical point for building a robust, anomaly-free database.
Hey, if this helped you finally wrap your head around some of these advanced concepts, do us a huge favor and hit that like button. Share it with anyone you think might find it useful, and of course, subscribe for more deep dives into topics just like this. And I'll leave you with one last thing to chew on. We just spent all this time talking about the highest levels of formal data purity. But let's be real. We live in a world of flexible schemas, of NoSQL, of schema on read. So does this kind of rigorous, upfront design still have a critical role to play? What do you think the right balance is? Thanks for watching.